deal with the variability that takes place in factories. And there are 3 weeks that are dedicated to the basics of probability and randomness. But the rest of the course uses those 3 weeks extensively. So almost every, well, let's say at least half of the weeks use probability as part of the lectures and to explain the results that we're using, where the formulas come from, and so on. So probability and randomness are very important.
Great. Can you just take us through what the course covers really quick before we move on to questions?
What week are we up to now?
We're still in week 1.
We're still in week 1. Okay. So week 1 is the overview.
Oh, sorry, we're on week 2.
Week 2. Okay. So we've started we've started probability. Probability and stochastic processes are, as I said, essential to what's going on in the course, in the rest of the course. I'm giving you a very, very short course in probability and stochastic processes there. Probability, you know, everybody knows what randomness is. There's a mathematical theory of it which formalizes things, which makes it possible to compute probabilities and to predict the probabilities of future events and so on. Stochastic processes describe events that take place over time, describe systems and processes that take place over time. So stochastic processes simply mean probability applied to dynamic systems that have random events taking place. Week 4 is about queuing theory, which is a special case of a stochastic process. Queuing theory is about, well, queuing is the term that refers to people waiting in line. And that was where this whole idea about inventory and other things came from. Inventory is simply material waiting in line, waiting to go to the next machine. So queuing theory uses the more general theory of stochastic processes to investigate things like that. In week 4, we present some very simple queues, which are not really realistic for factories, but which give you a good idea of the whole idea, give you a good idea of how random arrivals and random services affect things. So in week 4, we use some very, very simple models to explain that. But it's after that we talk about factory models. So week 5 is about inventory. And as I said, inventory is simply material waiting to be processed. Everybody still, oh, okay, we're still there. Inventory is material waiting to be processed. And we have control of that. So the week is about how you predict the performance of inventory and also how you manage it. And we're talking here about inventory that is subject to random events. And the random events that we're focusing on have to do with unreliable machines in factories and also random demand that changes from day to day and week to week and so on. Demand is not something that's smooth. It comes in different amounts of demand. Yeah, the customers demand different amounts of stuff from one day to the next, even from 1 hour to the next, if you're working on that time scale. So the problem with inventory is how do we manage inventory so that we have enough to satisfy demand most of the time, but we don't have too much inventory because inventory is a cost. So like everything else in engineering, there are always trade-offs. You can always get better performance in many cases. I shouldn't say always, but you can often get better performance as seen by whatever performance measures you have, as seen by the customer, but at high cost in some cases. So the performance measures that we deal with, for example, are whether there are stockouts. A stockout means that a demand arrives and there's nothing to satisfy the customer. There's nothing available, and we make the customer wait until the material, the thing that's demanded, is available. Now, we can reduce the frequency and duration of stockouts by keeping a large quantity of inventory. But if you keep a large quantity of inventory, there's lots of costs, and we talk about those costs in week 5. For example, there's a financial cost. You have to buy raw materials to make inventory, and then you have to invest effort, worker time and machine time and so on. So the inventory costs you before you can sell it. In addition, there's the danger of inventory spoiling or going obsolete. Oh, I see there's a question that somebody, whoops, wait a minute, there it is. In terms of inventory, do we focus on finished goods inventory or raw materials? Do we look at when to hold finished goods versus semi-finished inventory or raw materials? Also known as, what level in the bill of materials is it best to hold safety stock? That's a whole lot of questions from somebody who sounds like he knows a lot of inventory already. The answer is all of the above, but none of the above in great depth, because we're dealing with a lot of subjects here. So the question is, do we focus on finished goods inventory or raw materials? The answer is we deal with both. In addition, there's a third category, which is in-process inventory. We look at that as well. We're not looking so much at when to hold different kinds of inventory. That's a little bit more advanced. And the next, at what level in the bill of materials is it best to hold safety stocks? This is not a full course in inventory. Those are good questions. You can spend the full semester on nothing but inventory. So this course is really a kind of introduction. In fact, it's called Introduction to Manufacturing Systems. So we're not dealing with all those issues in detail. We're dealing with a lot of them. Okay, any other questions before I move on to week 6? I guess not. Okay. So week 6, in a sense, we're dealing with a certain kind. Well, we're dealing with a certain kind of manufacturing systems in detail now, and there will be in-process inventory. And here the issue is that we're making parts on a production line or transfer line. There are various versions of it and names for this kind of system, which is a sequence of machines with in-process inventory buffers between the machines. So material goes from machine 1 to buffer 1 to machine 2 to buffer 2 and so forth. It's a single part type, so all the parts are the same and interchangeable. This is appropriate for high volume manufacturing. And the issue here is simply the question of how much space do we reserve for inventory. The question is not how much inventory we hold, but how much space we devote to inventory. And as a consequence, how much inventory is actually going to be held in that space. And we focus on unreliability of machines. So when a machine somewhere in the middle of this line fails, the buffer upstream of that machine gains material if the upstream machines are working, and the buffer downstream of that machine loses material if the downstream machines are working. Eventually, those buffers could become full or empty, and when that happens, the failure propagates to the adjacent machines, and it can keep propagating if the failure lasts long enough. So the question is, what is the relationship between the machine reliabilities and the sizes of the buffers? By machine reliabilities, we're talking about the mean time to fail and the mean time to repair of the machines. So if a machine takes a long time to repair, we better have big buffers around it so that we don't let that failure, that stoppage, propagate to the adjacent machines. And so all that is dealt with in a lot of detail. It's based on the stochastic processes that I talked about before. The trade-off is that, oops, there was a question, but it disappeared. I'll get back to it if I can. If we have bigger buffers, we have higher production rate because the failures don't propagate from one machine to the next. But if we have, but having big buffers takes up a lot of space and can hold a lot of inventory, and those are costs. If we have small buffers, we can avoid those costs, but then we have a lower production rate of the system. And there was another question that popped up on the screen, but it's disappeared already. You want to put it back? Okay. Will we learn how to measure plant capacity for low volume, high mix? How to calculate capacity without consistency on structures, man hours? I view plant capacity as production rate, essentially. But when you have a mix of different part types, low volume, high mix, the high mix refers to a mix of part types. The short answer to your question is no, we don't go into the detail, but let me discuss a little bit about what the issues are. And some of those issues are dealt with in the first week. If you remember, so you're in the second week now. If you remember, I talked about how capacity in the first week, how capacity is not a single number when you have a mix of parts, but it's really a set in a high dimensional space. So that makes the definition of capacity hard to deal with. Now, there are people that focus on this, and as I say, this is a detailed issue and too detailed for the level that this course is at. Okay. So let me go on. Toyota Production Systems. This is something that that people need to know. And again, this is not you can spend a whole semester dealing with Toyota Production Systems, or possibly a whole year. I'm not going to do that. It's going to take place in 1 week. Toyota was a pioneer in very efficient manufacturing systems, very efficient management of manufacturing. And it's a very comprehensive system. We're only going to talk about a little bit of it, although I'm going to try to give an overview, touch on a lot of subjects that are in it. So I'm mostly focusing on movement of material, but I'm going to try, I have tried to cover all of the important parts. Toyota developed a very efficient way of manufacturing out of necessity. Back in, after World War II and up until the 50s and 60s, Japan was pretty poor, and but they had a good technical capability. The only way, though, that they could manufacture cars in a very efficient way was to use all their resources in the most efficient possible way they could. And in those days, everything was done manually. Everything was done on paper. There were no computers available to begin with, and they developed a tremendous way of moving material around and of keeping people busy in the right way. So the focus was on very efficient use of resources. One of the important things about the Toyota Production System is that they realized very early that people had to become very much involved in it. So there's a very human element of this, which again I'm going to gloss over in not too much detail. But the important thing is that people at all levels of the company had an input in how production was done. At the lowest level, at worker lines, the workers were able to observe how the production systems, how the machines and the strategy was working, and they had the opportunity to be heard by management. And that was, in some sense, pretty revolutionary all over the world at that point. Anybody in manufacturing these days, anybody in factories knows at least the name Toyota Production Systems and knows a little bit about the philosophy, but it's not always implemented as well as it could be. Okay, I don't think you need me to say anything about the final exam. So let's go on to the next question or slide or whatever.
Sure. Thank you for giving that overview. We do have one question. What kind of decisions can this course help me make during the course of an ordinary workday in a factory?
Well, first of all, the goal here is to give people who haven't seen factories very much, people who are interested in manufacturing but are not professionals yet or haven't really studied it in school, to give them an overview about what manufacturing is all about. And in addition, to give you some intuition about how factories behave and how material flow behaves. So there will be some specific formulas, for example, how much inventory to hold, and techniques about deciding how much inventory space you should have and so on. But I'm not so much focused on day-to-day decision-making as preparing you to understand what's happening when you set foot in the factory and to allow you to understand the factory much more quickly than you would otherwise. Great, thank you. Also another question. There's something just popped up here. At a high level, what is covered in 28542X, and how does it build or differ from this one? The answer is that it goes into a lot of things in a lot more detail, such as the single part manufacturing systems. The question is, how does production rate vary with machine reliability, buffer sizes, and so forth? And we give you some tools with Matlab to design factories or design small production lines in factories, and that becomes part of homework and exams. The other things that we deal with have to do with scheduling of factories. And we talk a little bit about some of the literature in scheduling. But as I say again, the most important thing is to develop the intuition and to understand how things relate to one another. Okay, other questions?
I think that's it for now. So we're a little low on time.
Oh. Yeah, that's because I was clumsy with getting my computer going. I can't.
That's okay. Technical difficulties happen to all of us. So let's.
That's very kind.
Let's finish up some of the questions answered or asked during registration, and then answer any last questions from the audience.
So the question with the without the answer, in what industry? In what industry?
Yes.
In what industry would this benefit the most, and how can the course be applied to various industries? Well, a lot of the material is focused on high volume, low mix manufacturing, but the mathematical and computational tools apply directly to that, but variability occurs in all industries, and I think it's very important for people to understand how variability behaves and how it affects factories. So that, in a general way, applies to all industries. Let's leave it at that.
All right, great. I believe I covered the cost of the course earlier.
Okay.
There is financial aid available on edX. So we encourage anyone who's thinking about verifying but is a little dissuaded by the course cost to look into that. I answered probability and uncertainty. So we just have this first one, Stan.
Let's see. Let me go to the second one. Will the course require Matlab programming and some other simulations? Matlab is used, but we're not requiring you to program with Matlab. In effect, we're providing you with some written programs that you can use, but if you know Matlab, you can take advantage of it and use those programs as subroutines, and that will help you do searching, mathematically searching for solutions, computationally. Did you already deal with the first question, or should I answer that one too?
No, please answer that one too.
Well, it says knowledge of principles in manufacturing builds a foundation for learners to confidently enter and improve manufacturing environments, and that's exactly right. Principles of manufacturing, the whole idea is to try to bring together what manufacturing is and what problems manufacturing engineers and managers have to solve to do manufacturing well. So my part of the course, my part of the program is to deal with systems. Other people deal with processes and with quality control, with supply chains and so forth. And some of the issues that I'm dealing with for this purpose apply everywhere. For example, the real enemy of manufacturing is randomness, and that's true everywhere. It's the enemy in the sense that that's what makes things tough to deal with. If there were no randomness, the problems would be much easier to solve. But of course, the whole point is that there is randomness, and you have to take that on. And so all of us deal with that in one way or the other. Possibly this course is the one that makes it more central than the others do.
All right, great. Just some additional resources really quickly. We skipped over some information about the course logistics, but all of that is in the syllabus, which is in the first section of the course. And for those of you asking about what the partner universities are for the master's program, that information can all be found at this website here. And of course, you can email the course team at any time when you have questions. So let's just wrap up by answering the last few questions in chat. I think, Stan, the first one is, what amount of theory versus practice do we have in the course?
The course is, I guess you could say, is mostly theory. It deals with examples, but there's no opportunity to visit a factory, or there are no labs as part of the course, and so forth. So I suppose it's fair to say that it's theory, but different people have different ideas of what theory is. You're not required to learn much mathematics in the sense of solving a lot of hard problems. There's some mathematics in the section on randomness, but it's not a theoretical math course. The mathematics that's in the course is there as a set of tools that are needed to understand randomness and to design systems that account for randomness. Other questions?
Can they use plant simulation for tasks in this course? I believe they need to use the Matlab provided.
You can use any tool that you like, that you have access to, but the Matlab tools are designed for the kinds of questions, and the questions were designed, I should put it the other way, the questions are designed for the Matlab tools. One issue about simulation is that we talk about simulation in the course. I think that's in the second part. Simulation has a lot of advantages in that it's very flexible, can deal with any kind of a factory, and you don't need to think about it mathematically in order to use it well. However, it's a clumsy tool in that it can take a long time to get answers, and it's based on random models, which is a good thing, but in order to get reliable answers, you have to run the simulation for a very long time. So in principle, you could use a simulation if you design it properly to solve the problems that we give you the Matlab tools to solve. But that would be a dangerous thing to do, and I don't recommend it, because we have a certain flexibility in how many in the accuracy of the answers that you get, and to get the answers that satisfy those requirements may require very, very long simulations. So if you have simulation, I encourage you to play with it and to compare the Matlab results with the simulation results and see how they're the same and see how they differ. But I would not recommend using simulation to answer those questions.
All right. We have another question. Is 6 hours per week, aside from the lectures, enough to pass the course successfully? We typically recommend 10 hours per week. That's usually the average we find in course feedback is what makes students successful. But if you have extensive background knowledge, you may get by with less time devoted per week.
If there's some material in the course that, frankly, you won't find anywhere else, and that's the detailed models of the flow lines, of the production lines. I don't think you'll find them anywhere else, and so you probably haven't seen them before, and so that's going to require a lot of thought. If you have a background in the other areas, you probably can get away with a little bit less time, but this does require a bit of a commitment.
All right. There's a question: is fluids production covered in the 2X course?
You mean things like oil refineries and so forth? Is that what the question is about?
I believe so, yes.
The short answer is no. Some of the principles will apply to that, but we stuck with discrete parts manufacturing just so that the scope would be limited, so we can say more details about specific things.
All right. Let me just double check what other questions are still waiting. Will the POM credential help me get a better job position?
Well, we certainly hope so. We've only done this for a couple of years, so we don't have a lot of feedback on that yet. But the MEng program, the Masters of Engineering and Manufacturing program, that the Principles of Manufacturing program is based on, that's the MIT Masters program, the face-to-face resident program. That's been going on for quite a long time in one form or another, and that has been very helpful for people getting jobs. And we've gotten lots of feedback about that, and people like it very much, and their bosses seem to like it very much. So this is only part of what's of that, but I hope that it will go some distance toward doing the same thing.
Okay. Let's see. We do have a question of, do you get a certificate for completing each course or just the 8? Yes, you do get a certificate for each course. And then when you finish all 8, you get the MicroMasters certificate. But you can just take one course and get a certificate saying you completed that specific course. And if we'll do any other webinars during the course, we will certainly try to see if we can. We typically do one before proctored finals in the 2X courses, and we will keep you posted on additional webinars. And Stan, I think there's one last question for you. Are there extra reading materials aside from the handouts?
There's lots of extra reading you can do, but we haven't included anything, I don't think, in the course yet. The short answer is no. You know, you'll be busy enough with this course, but if you have specific questions about things that you want to pursue, ask the helpline, and I hope that those questions will come to me, and I'll try to answer them. I don't routinely look at the helpline, but if there's a question that's directed to me, then I'm sure that will be brought to my attention. Are we done? I just wanted to say that I want to thank everybody for participating in the course and specifically for participating in the webinar. And I hope that there will be more webinars coming up so I can answer more questions.
Yeah, thank you, everyone. Thank you for sticking with us while we had our technical issues. There will be a recording of this webinar posted on the program forums later, so you can reference it as you want. And thank you, everyone, for attending.
Yes, thank you.